This second problem from chapter 13 has us using Henry's law to calculate gas solubility. So one of the things that is important to think about is just trends, particularly when it has to do with solubility, since this chapter is on mixtures. So we already had talked about the trend with temperature and solubility with solids. And for most solids, salts and so forth, the solubility increases as we increase temperature. And a classic example of that is thinking about dissolving sugar in water. That sugar is going to dissolve more easily in hot tea than it will iced tea. And an important trend to remember is that temperature trend is actually the opposite when we consider the solubility of gases in liquids. And I know sometimes it's difficult to think about dissolving gases in liquids, but a classic example is thinking about dissolved carbon dioxide, and that's what carbonates beverages. And so the trend is the opposite, that as we increase temperature, the solubility of the gas actually decreases. And we can think about this, that if we want a carbonated beverage to stay fairly carbonated, we want it to be cold. As you warm up a soda, it's going to go flat more quickly. And another example to think about this is if you just take some water and you begin to boil it. As you heat it up, you'll begin to see it begin to make some bubbles, and this will happen well before it's actually boiling. And the reason for this is that there are dissolved gases that are in the water, and as you warm up the water, those gases become less soluble in the water and they end up bubbling out. Okay, so actually moving on to this problem, and this is a fairly straightforward problem that uses the equation for solubility of a gas. So again, we're going to look at the solubility of carbon dioxide as a function of gas constant, Henry's gas constant, and the partial pressure of carbon dioxide. So again, this gas constant is going to be specific for the gas that we're talking about. In this case, it's carbon dioxide, and the solvent that we're talking about. And in this particular case is water. So this equation basically says the solubility of a gas is directly proportional to the concentration of the gas. Remember, that's how we measure gas concentrations, is in partial pressures. So the solubility of a gas is directly proportional to the concentration or partial pressure of that gas that we have above the liquid, and then it's proportional by this constant. So in this problem, they tell us that the partial pressure of carbon dioxide gas inside of a bottle of soda is 4 atmospheres. So that represents this value here, the partial pressure of carbon dioxide. And there's temperatures specific component to this. So this is at 25 degrees C. So we'd like to know what is the solubility of carbon dioxide, and they give us the Henry's law gas constant for carbon dioxide in water as 3.3 times 10 to the minus second mole per liter atmosphere. And again, it's important to note that these two temperatures are the same. So again, this is a very straightforward problem in this regard, that all the pieces of the information are given directly. So the solubility of the carbon dioxide is going to be equal to 3.3 times 10 to the minus second mole per liter atmosphere times 4 atmosphere, which is the partial pressure of carbon dioxide. Simple math for this, and we can see that, oops, I'm not going to cross out moles there. We're going to cross out atmosphere. We're going to be left with molarity, 0.1 moles per liter. So this is kind of what I would call a basic skill problem. Can you take an equation, in this case the solubility of a gas in a liquid, and kind of use it correctly and solve for the correct answer? Just to kind of elaborate on this problem a little bit and give you an example of how we make this problem a little bit more complex. One of the ways that it could be made more challenging is maybe, so let's say that this is, make it a little bit more challenging. What if the partial pressure of carbon dioxide is given in torr? Well, then you'd need to do initial conversion to make sure that our units are the same here. So that's just a little bit more of a challenge. What if the partial pressure of carbon dioxide had to be solved using PV equals nRT? Again, that's quite a challenging problem. That might be the kind of a problem you'd see at the very end of the chapter, where you have to apply previous knowledge in order to use that to solve an earlier problem. You might need to do some, stoichiometry or something with an equation. So there's kind of increasing challenges with some of these problems from a basic skill kind of involving earlier materials. There's also application, which again, maybe might provide an interesting application to this, but also utilize some previous knowledge. So for example, I might ask a question, how many grams of carbon dioxide are dissolved in solution here? And I'd have to tell you that maybe you have a half a liter bottle of soda. So in that case, what we do for this one is 0.1 moles per liter. And if I told you that you had a half a liter bottle of soda, that would tell us the number of moles of carbon dioxide that we'd have. And then you'd need to use the molar mass. So 1 mole of carbon dioxide is 44.01 grams of carbon dioxide. Solving that will tell us that there's 0.2 grams of carbon dioxide if we had a half a liter of this soda.